Hello all, I welcome you all to the second part of the 8th lecture. So previously we saw about phonons, its dispersion relationship and its behavior in the case when you have a monatomic chain or diatomic chain and so forth. Right? So now we will talk about optical absorption, and we will very soon see how the phonon dispersion will help us understand this and its relevance in our current course. Okay, so optical absorption, particularly it does not have to limit itself to the optical regime, because the electromagnetic spectrum is much wider, right? Electromagnetic spectrum starts all the way from few hertz, which will be our acoustic frequencies, audio and everything, right, up to few kilohertz, and then you have up to, let's say, 3 megahertz, some mid-range frequencies. From 3 megahertz to about 3 gigahertz you have ultra high frequencies, right? You have your semiconductor electronics working in this range. From here you have up to about 300 gigahertz extreme high frequency, right? You have a lot of microwave RF devices working in this region, and from here the electronics kind of saturate, right? You cannot work in such very high frequencies. Then you start having the terahertz regime, where most likely they are all optical components, in the sense they are all electromagnetic waves which does not deal with solid state devices, right? So up to about 100 terahertz you have terahertz radiations, and so to speak. Then you have this band of which we are particularly interested. It's called as the visible band. It starts from about 300 terahertz and go all the way to 800 terahertz. This is the optical visible light regime, and then you have X-rays, gamma rays, and so on and so forth on the other side, right? So these optical regimes, or the light in this visible range, or as well as in other ranges, right, it helps us in understanding the various physical phenomena that is happening in the semiconductor. One such experiment is which is routinely done, is that we have, let us say, a semiconductor under consideration, right? And then we have this source which can send out an unique wavelength. Wavelength and the frequency are related by E is equal to h nu, which is equal to hc by lambda, right? Lambda is the wavelength, c the velocity of light, and nu the frequency is what we're talking about. So this is the famous relationship, right? So you have the light which is incident on the sample, right, of particular length L, and then we measure the light which comes out by some spectrometer or some sensitive photodetector, right? We just see how much of the light which comes out. So typically it so happens that if I send out a light of intensity I, a portion of it is reflected back, which is called as R. R is the reflection coefficient, and the light in the material dies slowly because of absorption if the wavelength is particularly suited, right? And it was found, or it is typically found, that the intensity of light in the material varies in this particular fashion, is proportional to, let us say, some alpha being a constant. I is the intensity of that particular point. So the intensity reduces in this particular length x proportional to the actual intensity that is present, right? If such a relationship exists, then we can write the solution of it as some I naught e power minus alpha x, right? Alpha being the unit of 1 by centimeter. Alpha is called as absorption coefficient. Alpha is the absorption coefficient. It is the rate at which an electromagnetic light is absorbed in the material, right? So once we have something like this I naught is actually is I incident, right, into 1 minus R. R is the reflection coefficient, and you know that R can be obtained from Fresnel's equation, right? 1 minus NR square plus KE square by 1 plus nr square plus ke square. These are all still in the classical domain. You must have seen this many times before in your undergraduate courses, right? Where nr and ke are complex refractive index, which is defined as nr minus ike, right? And nr is just the ratio between the velocity of light in vacuum and the actual velocity of the light in the semiconductor, right? It's called as a refractive index. It's just the ratio between the light velocity in the vacuum and the light velocity in the semiconductor. And ke is called as the extinction coefficient, which is related to the absorption in the form is alpha into lambda by 4 pi. Right? Alpha being the absorption coefficient that we previously saw, lambda is the wavelength under consideration, and for typically it is written as alpha is equal to 4 pi ke by lambda, right? It's the same way to write either ways, and alpha is by centimeter inverse, typically written in centimeter inverse. Ke is called the extinction coefficient, right? So this particular extinction coefficient depends strongly on how the electromagnetic radiation interacts with the semiconductor, and this is the reason in which few semiconductors are optically transparent to the wave, or it absorbs strongly. It depends upon the band structure, as we saw before, right? So let us say that we have a semiconductor with a valence band. At 0 Kelvin, you see that the valence band is completely filled, right? And the conduction band can have multiple features. If it has a minimum at the top of the valence band, with the k value at the top of the valence band, we call it as a direct band gap semiconductor, right? But then certain semiconductors like silicon have a minimum which is not exactly at the top of the valence band, but then which is offset by a particular value in the K space, which makes them an indirect band gap semiconductor. And it is for these purposes that you actually need not only the energy of the gap, right, but also the an additional supplement from the phonon subspectrum, because you also have to match both the energy of the excited electron in the conduction band as well as the wave vector that is necessary to actually excite the electron, right? So under situations where you need this kind of phonon assisted excitation, you can see that E prime is actually E is the energy of the electron at the valence band, plus h nu, the energy of the photon, plus or minus E photon, right? So E phonon. So basically an absorption, this is basically an absorption process. The absorption process can either absorb a photon or emit a photon depending upon the energy of the photon in consideration, right? If the energy of the photon is much larger than the gap, so basically E dash minus E is typically equal to E gap, right? So E gap is typically h nu plus or minus E phonon, right? So basically you can have the photon which is much higher than the band gap releasing a phonon, thereby creating an excitation state, or you can have a photon much considerably smaller than the gap, absorbing a phonon to give you the excited state, right? Depending upon the density of the phonon that is present, each one of these processes are as likely, right? So this process determines the absorption or the absorption coefficient alpha. Right? In typical semiconductor, if I plot the absorption versus wavelength, alpha versus wavelength, you can see that there is no absorption till a particular value, and then absorption starts to sharply shoot up beyond a particular threshold, and that threshold is what we call as the band gap. And close to the band gap, you can see that the absorption increases strongly because you can have interband transitions. In many semiconductors, alpha is typically expressed as h nu minus Eg, right, power gamma, and this gamma is about half if you have a direct transition, right, and this gamma is equal to about 2 for an indirect transition. Right? So depending upon the temperature in which we are operating, because the temperature determines the phonon density of states, the absorption coefficient strongly changes for each semiconductor. So let us now stop for a second and then take a look at experimental values of this alpha for different temperatures and different wavelength. So here we have a plot of the absorption coefficient. Plot of absorption coefficient for different semiconductors. We have gallium arsenide, we have germanium, we have gallium arsenide and silicon, and you can see each one of them behave very differently, right? So germanium has the threshold starting at 0.6 eV, telling us that the band gap of germanium is smaller than gallium arsenide. We are just talking about these solid lines at 300 Kelvin, right? So you see that it raises sharply here. The one for germanium is here and the one for silicon is here. You can see that each one of them behave very differently with respect to how it starts, right? And you can see that the curve of this absorption is pretty soft, in the sense that it saturates much quicker in comparison to germanium and in comparison to gallium arsenide, which is a much steeper raise in the absorption coefficient, very close to the band edge. Right? At band edge, the gallium arsenide has a very strong raise in the absorption coefficient. That's primarily because of the fact that it's a direct band gap semiconductor, whereas silicon has a much slower raise because it is an indirect band gap semiconductor. And you can see that as the wavelength is increased, you can see that you have different transitions which are possible, right? Because you can see, let's say if this is the valence band and the conduction band has several dips, right? You can see that you have possibilities of excitations on the top of the valence band, as well as excitations from very close to the valence band at several levels to the valence band, and so on, right? So there are several options for this particular transition for an electron in the valence band to go to the conduction band, and hence you have a broad range of frequencies which will have similar absorption coefficients for silicon, whereas for gallium arsenide, very close to the band edge, you have a very sharp peak or sharp rise in the absorption coefficient, right? Yeah. So with this understanding of absorption in semiconductors, we will see what is the definition of excess carriers. Right? So at thermal equilibrium, we know that N into P equal to Ni square, where N is the density of electrons and P is the density of holes, and Ni is the intrinsic carrier density, right? And if it is N doped, then N is much larger than P, which is almost equal to Nd, right? And P can be written as Ni square by Nd. Right? However, if there is an additional excitation, then you can see that, let us say I take a semiconductor and then I shine a light of h nu larger than band gap, right? You can see that you will have additional del n and del p proportional to the intensity of the light which was falling, right? If the if the photon energy is larger than the band gap, then you will have del n plus del p. However, if the semiconductor is n type, del n is much smaller than n, and hence, which is the actual carrier density does not, the actual electronic density does not largely change. However, del p could be almost in the order of p, and hence del p starts to become dominant. The changes in hole density starts to become more dominant, and this change is what is called as excess carrier. And it is this excess carrier, basically E is n into p minus ni square, which is n into p plus del p minus ni square, which is n into del p, right? Because np is ni square, which is n naught p naught, right? So this is the excess carriers, which is which undergoes recombination and generation, as we have seen before, right? At recombination, whether it's direct recombination or tripartite recombination, and all these dynamics that we have previously seen, right? So we will stop here, and this is the some basic introduction into the electromagnetic interactions with semiconductors. The next time we will meet, we will deal some examples of continuity equations and so on. Okay, we'll stop here. Thank you.